Because we started talking about synthesis, but that homework just kind of comes out of left field and says do this, and so we definitely want to go through a lot of examples of that today. Also, if you didn't notice, I changed the homework a little while ago. It had 4 questions. I've gotten rid of question 4, so you're just going to do those first 3 questions in there. Question 4, it turned out, would have been impossible to do, so I decided to cancel that one.
How would it be impossible?
Well, not impossible, but you have to do a K-map with 5 input variables, and that's beyond the scope of what we're trying to do.
Three-dimensional K-maps.
Yeah, 3-dimensional K-maps. It's fun. You just get some boxes and markers.
Just out of curiosity.
Yeah, go for it. I mean, it's doable. It's just I didn't want people to get bogged down with those details. But in the section where we talk about K-maps, there is some material that we didn't go over, which is on compressing K-maps. And you can take a function of 5 variables and treat it as a function of 4 variables, where one of your variables appears in the outputs. And then you can use, a plain old 2-dimensional K-map to tackle that. But I wanted the focus to be on state machine synthesis, and that would have been a whole extra sort of piece of the problem. All right. Well, I'm going to say probably this may be all the crowd we get. So if you want to go ahead and talk about the Aerospace Club, and normally I record my lectures, so I'll give you an option. If you'd rather I don't record, I'll turn off my recording. Otherwise, I'll leave it in there, and then people who missed the class will be able to hear about it later.
Yeah, that's okay. Just leave it on.
Okay. So give me one sec. So do you want to share your screen?
Yes.
Okay, let me make you a co-host, and let me turn off my screen sharing. And yeah, you can just go ahead and take it away.
Okay. Give me 1 second. Let's see. All right. Hello, everyone. My name is Sophie Lin. I'm a professor from the physics department, and currently I'm also one of the 2 advisors for the Aerospace Program at Clark. So today I'm here to tell you a little bit about this program. The Aerospace Program was funded by the ASCC student government, and from my perspective, I think is one of the best extracurricular programs that you can find at Clark College. So depending on the funding and how many students were involved, typically the program has the capability to host and build up to 4 individual teams. And this year, due to pandemic, we have 2 teams. One is the ESI team, which is also called the Rocky team. Another one is AUBSI team, which is also called the Drone Plane team. Currently, the Rocky team is working on building and designing rockets. For this year, the team is working on a payload project through a workshop called the Rockon Workshop. And just yesterday, the team has just finished their project, and they're about to send their project to Colorado for a real flight test. Some of the members in this team are also working on something called the Level 1 Rocket Certification. So through the certification process, you will learn the knowledge and the skill that you need to know in order to design and build a rocket. This summer and then next year, the team plan to build even a higher level rockets and payloads. And hopefully by June of next year, we plan to travel to southern New Mexico and compete at events. It's actually an international competition event called Spaceport America, as you can see on the website. It turned out that for these competition events, there will be more than 100 teams and more than 1,000 students and faculty who are going to collaborate and compete at these competition events. And I also want to point out that actually Clark Aerospace is one of the few community colleges that were able to participate and compete at this level of competition events. Our second team, the drone team, is currently working on designing a drone that is capable of autonomous flight, navigation, remote sensing, and all different kinds of tasks. So for this team, their plan is that next year, also by about June 2022, they will travel to attend another international competition event, which is called AUBSISUAS event. And actually, on the website, you can also find a picture of the events that our team have traveled to. So if you look at the website, just right next to the, I think it's right next to the, or after the Turkey flag, you will be able to find maybe our team members. So, so this is another event that we are going to travel to next year. And again, Clark College is one of the few community colleges that will that can compete at this level of events. So, yeah, many kinds of benefits you can gain from this kind of experience and this kind of events. For example, you'll get to meet people who are also interested in aviation, and you also get to network with people and companies, so that you can build your career in this industry. I also want to say that through the projects we provide with the program, you also get the chance to work with your peers, your advisors. You get to practice and learn how to build your personality and characteristics, which I think is very important for your future work. Actually, it turned out that for the past 10 years, we have had students who have had find jobs in companies and organizations such as Boeing Company, Institute, and even NASA. So, so there's a lot of opportunities and experience we can provide from this program. So, and I also want to mention that actually this summer we plan to schedule several events and trip to flying museums such as the one at Evergreen and the one at Seattle. We also plan to organize several workshops, and in this workshop, you will get opportunity to learn how to design and how to build a drone plane or a rocket, and we'll also show you how to design and do 3D modeling using the 3D printer we have in our program. So there are lots of fun and interesting and exciting opportunities, events, and experience you can find through this program. So if you're interested in our program, please email me. I'm going to type my email address in the chat. All right. So please email me so that I can involve you in all these different kinds of experience and opportunity. Yeah. So that's my introduction. Any questions about the program? Any questions?
I have a question about which physics classes you teach.
Okay, all right. Right now I'm teaching several different kinds of courses. One is called the Physical Science 101, which doesn't have any prerequisite and is open to all the students from Clark. But I'm also teaching a calculus-based course called Engineering Physics. And I'm teaching the lecture, the calculation, and the labs. So I'm not sure if any of you have taken their classes or you plan to take the class. If so, I would love to see you in my class.
I think I have a few of those.
Okay. All right. Good. Any other questions? Okay, I noticed there's a question from chat. Do you have to be part of the aerospace degree program? No, you don't need to. Actually, the program is open to all the students from Clark, so you don't need to major in computer science or engineering or physics in order to be a member of this program. We provide opportunities for students to not just learn how to design and work on an engineering project, but also we give students opportunity to do some, say, outreach job that is also very important to our program. So there are lots of interesting things and different kinds of responsibility you can find in this program. So, all right, did I answer your question? Any other questions?
No, thank you.
Okay, thank you. And thank you for the opportunity to talk to you guys. Thank you. Have a good class.
Thank you so much, Sophie. Definitely appreciate having someone from the club come and talk about this, because it really is a fantastic opportunity. So
Yes.
so yeah, thanks for doing that, and hopefully we'll get some response from it.
Okay, all right. I look forward to your emails, guys. All right, bye. Have a good class.
Thank you.
All right, see you later. All right, so yeah, if you've taken my 101 class, you hear me talk about opportunities and how, it's difficult to create opportunities, but what we do have in our capacity is the ability to take advantage of opportunities if they come along. And this is potentially a huge opportunity. I've had students in the past who have taken this, and with no background in rocketry or aerospace or anything like that, just kind of said, yeah, I want to work with rocket scientists. I'd love to be a rocket scientist, and got involved with the club. And one of them, you know, really, really threw themselves into it. Ended up being, I think, president of the club. Ended up in Huntsville, Alabama, after one of the competitions, sitting next to like a program manager from NASA, who handed her a card and said, "When you graduate, give me a call. You've got a job if you want it." I mean, it's really it's a chance to sort of put yourself out there, and if you feel passionate about exploring this kind of area and working on it, there's so much to do. And if digital logic is your thing, there's tons of opportunities. If programming is your thing, if writing is your thing, if sewing is your thing. I went in one day over spring break a couple of years ago, and there was a team of about 6 people, and they were sewing the parachute that was going to be used for one of their test flights. Right? This is a complete start to finish kind of endeavor, and it's all students, right? Faculty members are there to sort of help and advise, but the whole project, the whole work, the planning, the documentation, all of that is done by students. And you can find yourself competing with engineers from MIT and Stanford and Caltech, and you can find yourself, at NASA facilities, or other organizations, showing off your stuff, and that's just really cool. So if it's appealing to you, definitely shoot Sophie an email and reach out and see what's going on. It's a cool opportunity, and it was the stuff outside of the classroom that really kind of shaped my experience when I was in college. The classes are good, but there's so much more to being in college too. So hopefully, if that's interesting to you, you can find a way to take advantage of it, or at least find out more information. So that's my additional sales pitch on the club. All right. So let's talk about Lab 5 a little bit. So Lab 5, you were working with the 555 timer, and you were hooking it up to a counter, and then hooking the counter up to a 7-segment display. So you end up with a system that just kind of on its own counts every couple of seconds from 0 to 1 to 2 up to 9, and then either goes back to 0 or goes blank and then goes back to 0, and then either hangs up or continues counting. but it's doing something on its own, right? It's not like you have to flip switches. And you could take this to a family member who knows nothing about engineering, and they could look at it and say, "Hey, you made something that counts." So it's kind of a fun circuit in that sense. So really good work on the lab. A lot of people got their circuit working. The lab reports looked really good. So pretty happy with that, and the lab grades kind of reflect that level of performance that I saw. So a few things I want to mention. Just to think about going forward. So one thing is, did your circuit work? So I saw some reports, they might have been like 15 pages, and they had everything I wanted to see. They had, introduction, description, experiment 1, calculations, timing diagram, circuit diagram, experiment 2, now we're going to do this, we're going to add this in. Here's a wiring diagram, here's a picture of my circuit. And then it just ends. And it's like, did your circuit work? Right? All of that is building up to, and here's the circuit that I designed, and here's the implementation in Tinkercad, right? Well, what happened when you ran it? And a lot of times, you build it and you test it and it works, and you're like, great. And so you put in the conclusions, new experiment, and you're done. Don't forget the punchline, right? Which is, I implemented this in Tinkercad and I ran it and it worked. Here's what I observed. Right? So part of the lab, you're supposed to include a test plan, which is, for lab 5, we said it's mostly just, standing back and watching to see if it counts every few seconds from 0 up to 9 and back to 0. So just put in one sentence, right, saying, observations and state in there, circuit worked as expected. So that's kind of a punchline thing. Next thing, make sure if you include anything in your lab that's not your own that you cite it. So there's a 555 circuit in the lab assignment itself, and I said that's you can take that and use it in your report. But if you do that, put a little note right underneath the picture saying taken from lab assignment 5 engineering 270. Maybe put in the URL of the web page it comes from or something like that, just so that somebody doesn't come back to you and say, hey, here's this thing you wrote. It's got your name on the front. This picture is exactly the same thing as in this document written by somebody else. That's plagiarism, right? Now, I know you're not plagiarizing, and I told you can go ahead and put those in. It's just a habit to get into. Because somewhere down the road, right, you might do this in something that you submit somewhere else, and they might look at it and say, hey, wait a minute, that's not your original work. I wonder what else in here is not your original work. So always put citations in. Right, it's just a habit to get into, and most of the time when we write technical reports, a lot of what we write is not our own because we're building on what other people have done. Somebody might take your lab report and come up with their own new experiment and write a report on that, but they might include parts of your report, but they would put a citation in there, right? A footnote or a link to a bibliography saying, this is taken from so-and-so's Engineering 270 lab report, and so on. So put citations in. Comment on the new experiments. I'm seeing a lot of really good new experiments, so that's fantastic. That suggests that people are thinking more deeply about what they're doing in here and really thinking about, so what else could we do? So I saw people modulating the 555, playing around with resistor capacitor values, seeing what that did. Trying to make something that would count backwards. I mean, all kinds of interesting things. So that's really cool. Keep up the good work on the new experiments. And then the only other thing I wanted to make a comment on, this is a general comment about timing diagrams and waveforms. So if you're asked to draw a waveform, and let's say you wanted to draw the waveform from experiment 1. So it's high for like 1.4 seconds. And it's low for 0.7 seconds. And so you can draw, a picture like this, and I know what's going on there. But if I didn't know what's going on, what would make this a little more useful is to show a few waveforms. Right? At least enough so that you can see that there's a repetition here. Because when you draw this, what happens after this? Maybe this. Or maybe this, or maybe this, or maybe this. So if you draw a few cycles and then you mark one of those as 1.4 seconds and 0.7 seconds. Now somebody looks at that and they see, oh, okay, this looks like it's repeating, so this must be a periodic waveform. So put in enough information to show, what happens after and before the things that you drew. And if you make, at least 2 cycles, then somebody will reasonably say, oh, this is a repeating pattern. Right? So none of these things are biggies. And they didn't cost you points in general, but just things to keep in mind for future reference. Any questions about Lab 5?
Are we going to do more with 555 timers?
So you're using 555s in Lab 6. So yeah. And in an in-person 270 class, we actually use them in 270 also. I don't think we kept that lab when we moved online for 270. But if you do any other engineering labs, you'll probably encounter 555s. They really are kind of like super common.
Are they just made of capacitors, or do they have an oscillator, like an oscillating crystal?
Oh, well, we can actually look at the data sheet.
I was curious because I had like an argument with my dad over, is it just a crystal oscillator or is it just capacitors?
What did he say?
He thought it was just crystal oscillators.
So
it was just like an array of capacitors that were like
there
the timing.
there actually is not a crystal inside. It really is just done with resistors and capacitors and transistors. Wow, I don't know why I can't get to TI's website. But I think they'll put a picture of it in here. So here's a simplified schematic. So buffers and, oh no, that's not right. Oh yeah, okay. So a pair of buffers, those are just kind of like inverters that don't invert, but with an inverted input. An SR flip-flop, an output buffer that just protects the output from the input, and a transistor. And it's this path right here which gives you feedback. And if you have feedback, you have potential for oscillation, and that's really what this is doing. There's no crystal inside, so this is a pretty approximate way to generate a waveform. And if you build a 555 circuit and you hit it with like compressed air to cool it down, you'll usually see a change in the timing waveform. If you heat it up, you'll see another change. If the power supply changes, the frequency may change a little bit. It's not super stable, whereas if it had a crystal inside, it would be using the resonance of some material like quartz to lock in a particular frequency of oscillation. So this is using what's generally called an RC circuit. And with a single resistor and a single capacitor, you can make a pretty simple circuit that if you analyze it, you'll find the output changes over time. It comes out as some kind of sinusoidal function. And with a 555, we run the output through a digital device, which will basically change the output to be either high or low. So it would take a sinusoidal output, turn it into that rectangular wave. And it's a pretty clever design. And like I said, when the person who came up with this first proposed it to his boss, the boss was like, well, why would you want to do that? You can just build it with a few chips, right? So you could get components for each of these things and put it on a proto board and have the same thing. But he wanted to do this in a little 8-pin chip and sell it for $1 or $2. And different packaging made all the difference. I mean, everybody wanted one of these. They couldn't keep them in stock. And people went to jail for like stealing these from their manufacturer and selling them on the black market and things like that. So it was pretty phenomenal. I don't think they have a deeper. No, so engineers don't usually get rich from things like that, unfortunately. But he's pretty famous. Um, and certainly a measure of immortality because, you can get a T-shirt with a picture of a 555 on it, right? So that's kind of cool. I don't remember why it's called a 555. I think there was a good reason.
Seems like it would be a resistor capacitor value on multiple times.
That could be. So like Hackaday has periodic 555 design contests. Um, and you can go through past ones of this, and people will make adding machines and synthesizers and things that exercise their dog when it gets bored, and all kinds of weird things using just a few or many of these 555s. Yeah, totally. That should be like the official shirt for engineers and engineering students at Clark. That would be pretty cool. All right, so how about Lab 6? How's that coming along?
I'm probably gonna start it today or tomorrow. I'm definitely gonna try to start it before the weekend though.
Okay, cool.
Yeah.
I'm probably gonna try and see how it should behave in like a logic simulator, maybe,
Okay.
for fun.
Sure. That sounds cool. And
Some really cool ones of those.
yeah. And we talked about this on Tuesday, right? This is your Lab 3 permission circuit using the green output. This is the 2 to 4 second delay, which means this box right here has got some pieces in it. It's got a 555 timer, and it's got a pair of flip-flops. And you're going to need 3 of these circuits. You can use one 555 for all 3, though. In fact, you're better off if you do that. So have one 555 that feeds the delay circuit here. Use that same 555 to feed the delay circuit for east, and then the same 555 to feed the delay circuit for south. So you end up with one 555 circuit, a total of 6 flip-flops, a total of 3 sets of combinational logic for doing this, and then your original Lab 3 circuit for generating 3 green signals. So it's a lot of pieces, but they go together pretty painlessly. And you're in Tinkercad, so it's harder to accidentally pull your wires out of your board by mistake. So that's good, because this gets to be a nightmare in the actual lab, and especially if you can't get it done in one setting, because then you've got 3 protoboards wired together sitting in your parts box, and you're just hoping someone doesn't come along and mess with it. So Tinkercad actually works a little bit better here. All right, other questions, comments? All right, let's do some more state machine synthesis. And let's do an example that involves JK flip-flops, because JKs are special, and they give us an opportunity to take advantage of this idea of a don't care in a truth table, which works nicely when we do our K-maps. So let me draw, as a reminder, what a JK flip-flop does. So J and K are 0, the output doesn't change. 0, 1, the output's a 0, 1, 0, it's a 1, 1, 1, the output toggles. So this is showing the new value of the output after the clock ticks based on the current value and the J and K inputs. So we'll refer to this a lot. And we'll make a variation of this table also. So let's try and synthesize a circuit. So we'll go with 4 states. And I don't know, I'm going to make this up. So there's our input X. We're going to have one input. I'll go ahead and put some outputs here. I'm not too worried about outputs. So this is a mealy or a Moore machine?
Mealy?
One more guess.
I thought it was a more.
It's a Moore machine. So a Moore machine, the output depends only on the state. And here, knowing what state it's in, we can tell exactly what the output is. So we'll call the output Z. So this is a Moore machine. It's just a definition, right? So if it only depends on the state, it's a Moore. If the output depends on the inputs, it would look up as a slash on each of these arrows with the corresponding output value. That would make it a Mealy machine. So this is a Moore machine. So and we're going to use JK flip-flops, and that's because that's what we're given, right? We're told we have to use JKs. But we could do this with Ds, we could do it with Ts, so we're going to use JK flip-flops. So we'll make our usual state assignment table based on the values of Q1 and Q0. And, you know, we don't have to do it like this. I could call this S11 and I could call this S00 and so on. These are just names. But what I'm doing here is I'm saying, you know, if we're in this state, I want Q1 and Q0 to both be 0. That's how we're going to designate this state. And if we're in this state, 1, 0, I want Q1 to be 1 and Q0 to be 0. So I've started designing my machine already. I've decided what the values of my 2 flip-flops will be corresponding to each of these states. But once you have this information and this, now we can make a transition table. And from the table, we'll be able to make a truth table, and we'll be able to make K-maps and equations and then build a circuit. So this is a lengthy process, and I recommend working with pencil. Pencil doesn't show up as well on here, so I'm going to live dangerously and use pen. And so first thing we want to do is take this transition information. This says for a given state and a given input, what's your next state, what's your output. We're going to put that much into our table form. So we're going to start with state. And we're going to express that as Q1 and Q0. And this corresponds to the present state of the system. And we have one input, which is X. And so let's start by enumerating these. So right, just finding all the possibilities. So these first two, these correspond to the state we're calling S00. These next two are the state we call S01. And then S10 and S11. All right, this is a good place to go ahead and put in the output. And whether this is a Mealy or a Moore machine, if you know the present state and the input, we should be able to write down the output. Now, if it was a Mealy machine, for example, right here, if I had, you know, a 1, that means if you're in state 0, 0 and your input is a 0, your output should be a 1. And I would put a 1 right here. But for a Moore machine, it doesn't matter what the input is. Anytime I'm in state 0, 0, my output's a 0. So I can write a 0 in both of these rows, because those are the two rows corresponding to state 0, 0. And state 0, 1, the output's also a 0. State 1, 0, it's also a 0. And then state 1, 1, the output should be a 1. So there's our output column. And now I want to write down what the new state's going to be. So this I'm going to read from the table. So if you're in state 0 and your input's a 0, your new state is also 0, 0. If you're in state 0, 0 and your input's a 1, your new state is 0, 1. Alright, so 0, 1, input's a 0, what's your new state?
0, 1.
0, 1, good. Alright, 0, 1 and your input is a 1, what's your new state?
1, 0.
1, 0 right there. Sorry, 0, 1 and your input's a 1.
1, 1.
Yeah, state's 1, 1. Alright, how about 1, 0 and input's a 0?
0, 1.
0, 1, 0 takes you right back here. And 1, 0, input's a 1.
0, 0.
0, 0. Everybody seeing this? And then the last state, 1, 1, if your input's a 0.
Back to itself.
Back to itself, back to 1, 1. And finally 1, 1 and your input's a 1.
1, 0.
That takes you over to 1, 0. Alright, we're done with the diagram. We've got all this information captured in here now. One more thing to translate.
You need to come up with the equations, right?
We need to come up with the equations, but before we do that, let's fill in what the new values of Q1 and Q0 are. Now, I already said next state over here, so these mean the next state. But we can also put a little plus on the top, just so we don't get these confused with these. So let's put in what the new values of Q1 and Q0 should be based on what state we're in. And this is just reading from this state table that we made. So if we want to be in state 0, 0, that means Q1 should be a 0, Q0 should be a 0. S0, 1 means Q1 should be a 0, Q0 should be a 1. And that'll be the same here. And S1, 1 means Q1 and Q0 are both 1s. Here's another 0, 1, S0, 0, they're both 0. There's another 1, 1, and then S1, 0 means Q1 should be a 1, Q0 should be a 0, so this will be 1, 0. Right? And it's pretty clear what I did here. I chose the names of my states so that the subscript would be the value of Q1 and the value of Q0. So I can actually just look at this and write these down. But what we've got now is basically, you know, if we're in this state, in other words, if Q1 and Q0 are both 0, and our input is X, the current output's going to be a 0. And when the clock ticks, what we want to have happen is Q1 becomes a 0 and Q0 becomes a 1. And if those are the new values of Q1 and Q0, now we're going to be in state S0, 1. So that's going to achieve this transition. If we're in state 0, 0 and our input is a 1, when the clock ticks, now we're going to be in this state. Right? It's a state of mind, literally. It's just, you know, what are the values of the flip-flops? That determines the state. If we were writing a program, these would be variables. And we could have, you know, an integer that goes from 0 to 3 and says what state our program is in. And maybe in state 0, when you click the mouse, one thing happens. In state 1, when you click the mouse, something else happens. So you'll encounter state machines and the idea of state machines in programming, and other areas as well. All right, so does everybody have some sort of developing intuition about what this table is all about, why we care about this, and how it kind of relates to this, not mechanically the way we fill this in, but sort of from a higher level, how this is describing the movement of this machine from one state to another. Is that starting to click a little bit at least?
It clicks, but I think practice versus theory is going to go a long way.
Okay, yeah.
Yeah, I think another thing that's helped me a lot is just trying to think of it more, because like at first when I was thinking about this, I was trying to figure out like the flow of where the electricity was going.
Mm-hmm.
But I realized that that's really not the way to think about it. You gotta just need to think about it in a higher view, like you said.
Exactly. Yeah, that's a good observation.
I haven't checked the homework yet, but basically we start from the bubble diagram, right?
Correct,
State
yeah.
diagram, and then we gotta work our way after this. Okay.
Yeah, so the homework I think was this, and it's 3 questions. Build a machine for this using D flip-flops, build a machine using T flip-flops, build a machine using JK flip-flops. So the same diagram, and you just come up with 3 different implementations.
What was the last question?
The last one was changing the encoding to what we call one-hot encoding. But for 4 states and 1 input, you end up with 32 rows in your transition table, and that seemed too extreme. But we'll do a one-hot encoding example in class. So here's a cool thing to keep in mind. Have I done anything yet that's dependent on the fact that we're going to use JK flip-flops?
No.
No. So since you've got 3 questions all using the same diagram, this part of your table is going to be the same for all 3.
Okay, so we don't have to like remake the table 3 times.
Well, you'll want to remake it because we're going to add extra stuff over here, but you don't have to rethink it, right? If you work it through each time, it's going to end up looking exactly like this up to this point.
Okay. Sweet.
So that can save us some time. The JKs come in at this next step, and the next step is how do we make it so that when you're in this state and your input is a 0, the new values end up like this. But if you're in this state and your input is a 1, the new values end up like that. How do we cause that to happen? And that's about setting the inputs to the JK flip-flops, or the D flip-flops, or the T flip-flops. Now, if we had D flip-flops, the answer is easy. If we want the output to be a 1, set the D input to be a 1. If we want the output to change to a 0, set the D input to be a 0. For a toggle flip-flop, it's almost as easy. If the current output is a 0 and we want the new output to be a 0, don't toggle. Set T equal to 0. If the current output is 0 and we want the new output to be 1, we do want to toggle. Set T equal to 1. For JK, it's a little more complex. So let's think about just flip-flop 1, Q1, and the new value of Q1. And let's think about J1 and K1. And we'll keep in mind this table of how JKs work. And so let's work on the first row. So the first row, we want our new value of Q to be a 0. We're only looking at the new value of Q1 and the old value of Q1.
Why do you do 1 before 0? Like, I know like programming and stuff, it's always, everything starts at 0 normally. And so I don't really understand why starting at 1 and then doing 0 seems to just be, I mean,
It's
engineers or programmers.
it's fairly arbitrary, but when we do programming and you have like a 7-bit number, we number them like this. Sorry, an 8-bit number, right? This is considered bit 0, this is considered bit 7. And the reason is, you know, if this is bit number I, its weight corresponds to 2 raised to the I. And if we have an 8-bit number and we want to treat it as a 16-bit number, we simply add on more bits and make all of those 0. Now, if we number in the other way, if we treated an 8-bit number like this, and then we tried to put this in a 16-bit number, which looked like this, right? Bit 7 would no longer be bit 7. Bit 7 would become bit 15. Bit 6 would become bit 14, and so on. Whereas here, if we had, you know, a 16-bit number, bit 0 is still bit 0, bit 1 is still bit 1. So that's one of the reasons that in computer science we number the bits starting with a 0 on the right. The least significant bit is bit 0. It's not 100%. Right, there are times when you can find things numbered with a 0 on the leftmost position, but almost across the board in computer science and in digital logic, you're going to find the 0 being on the least significant bit in the rightmost position. You don't get the wrong answer if you do it differently, right? I mean, if I did Q0, Q1, Q0, Q1, J0, K0, J1, K1, right, I'll get exactly the same answer in the end. The most important thing is to be consistent in your own domain. So if you want to do 0, 1, make sure you do 0, 1 everywhere. T0, T1, D0, D1, that kind of thing. Does that make sense?
Yes, it does. Thank you.
All right, cool. You're welcome. All right, so let's think about JK flip-flop, and looking at this first row, the current output of the flip-flop is a 0. And we're going to tick the clock, and after the clock ticks, we want the output to remain a 0. So what should we set the J and K inputs to so that after a clock tick, the output is a 0?
It would be 0 or don't care, right?
Why?
Because 0 is both, it satisfies the condition when J is 0 and K is 0, and it also satisfies the condition when J is 0 and, sorry.
No, you're right. J is 0 and K is 1. Yeah. So if you look at this row, it says if J is 0 and K is 1, the new value of the flip-flop is going to be a 0. That's what we want. So certainly putting in a 0, 1 is going to cause this behavior. But it also turns out that if we were to put in a 0, 0, what does that say? It says don't change the flip-flop. Well, since the flip-flop is a 0 right now and we want it to stay a 0, we could also put in a 0, 0. So either one of those two combinations of J and K will cause this effect, which is the new value of Q1 is 0. And that's what's going to make JK so much fun to design with. Because since, you know, we know that J has to be a 0, but K can be a 1 or a 0, we don't care which. So the entry we can put in here is actually make J a 0, and K doesn't matter. It's a don't care. And the second row is exactly the same. Q is a 0, we want the new value to be a 0. So that's also a 0 and a don't care. And at this point, I like to go through and find all the cases where we're going from a 0 to a 0, so I don't have to rethink it. That's a 0 to a 1, 1, 1, 1, 1. Right, so all three of these we can just say 0 and don't care. But let's look at this fourth row now. So the current value is a 0. We want the new value to be a 1. So we want Q to become a 1. So what value should we put in for J and K?
1 don't care.
We could do a 1 or a don't care. Because again, if we do a 1, 0, that says make the output a 1. Hey, we succeeded. But if we do a 1, 1, that says toggle the output. Well, the output's a 0. If we toggle it, we're going to get a 1. Hey, we succeeded again. Either one of these will work for us. So making J a 1 and leaving K either a 0 or a 1 doesn't matter to us. That's going to get us happiness. So this is going to be a 1 and a don't care. And anytime we want to go from a 0 to a 1, we can use a 1 or a don't care. Well, we don't have any other cases like that. But our next case is we're going from a 1 to a 0. So how do we make the output of our flip-flop a 0?
It would be don't care or 1, right?
So if we have a 0, 1, that always says make the output a 0. So that'll work. If we have a 1, 1, that says toggle, which will toggle the 1 down to a 0. So 0, 1, 1, 1, either of those works. So this is a don't care 1. And the same thing here. All right, and then one more case. We want the output to be a 1. What are our options there?
Don't care 0.
Yeah, we can do a 1, 0, which makes the output a 1. Or we could do a 0, 0, which says don't change. It's currently a 1, just leave it as a 1. So K has to be a 0, but J, we don't care if it's a 1 or a 0. So don't care 0 does what we need here. All right, questions about that? That's the real trickiest part of this whole process, is getting these J's and K's set up correctly, or the T's or the D's or whatever the flip-flop inputs are.
My question is, how do we know where? So if we have an output from Q1 and Q0, we need to make sure that to get to the next state, J1 and K1 have to be something. Well, how do we know what we're going to feed to J1 and K1 to get these to the next state?
It's a bit of a reverse engineering of what the flip-flop does. So for example, down here, this last row, we want the output to be a 1. Right, we're still just looking at flip-flop 1. We want the output to be a 1. So you look at your table and you say, how can I make the output a 1? And the most simple choice is just set J to 1 and K to 0. And this table tells us if J is 1 and K is 0, tick the clock, Q is going to be a 1. Right? So putting in a 1 and a 0, that would absolutely work. And with JKs, we're just going a little bit beyond that and saying, oh, you know what? Also, if I did a 0 and a 0, that says leave the flip-flop unchanged. We want the output to be a 1, but it's already a 1 because we're in this state where this output is a 1. So if we say, set the inputs to 0, 0, that will not change the output. The output will still be a 1. So in the case of JK flip-flops, we get two possibilities for the J and K inputs. For a D flip-flop or a T flip-flop, there's usually only one possibility. But it's really just kind of looking at what's going to happen when the clock ticks and then saying, well, what should I set the inputs to? Well, if I set the inputs to 0, 0, my new output will be the same as the old. That'll be a 1. If I set the inputs to 1, 1, then when I tick the clock, Q would change. It would become a 0. That's no good. So I don't want to use 1, 1. And so you can go through the four possibilities and see, oh, either a 1, 0 or a 0, 0 will get me where I want. So you just write that as a don't care and a 0.
So for a Moore machine like this, we can basically look at, okay, well, J1 and K1 need to be a don't care and a 0 to get to the next state.
Mm-hmm.
So we can take whatever the output of present state of Q1 and Q0 is and arrange that to the inputs of J1 and K1 to be the next state.
Exactly, yeah.
Okay.
So that's what we're going to do next, is we're going to basically write equations for J1 and K1 in terms of Q1, Q0, and X. And then do exactly what you described, basically build a circuit so that given this will be the values for J and K. All right, so let's go on to J0, K0, and I'll show you a trick, and you'll see this in the book, and I don't want you to get bogged down by this. If it doesn't make sense, you don't need to do what I'm going to describe, but it can save us some time. So we're going to do J0, K0, right? And, you know, first row I want to go from a 0 to a 0. Well, didn't I already do that once? It seems familiar. Oh yeah, back here when we did J1, we had a 0 and a 0, and we came up with a 0 dash. So I guess in this case, going from a 0 to a 0, that should be a 0 dash. And is there any other case where I'm going from a 0 to a 0? Yeah, down here in the 6th row. So I can make that a 0 dash. And up here I want to go from a 0 to a 1. Well, that sounds familiar too. I think we did that somewhere a few minutes ago. So let's see if there's a space. This 4th row we went from a 0 to a 1. And we worked through, you know, what a JK flip-flop does, and we decided, oh yeah, to go from a 0 to a 1, we can do a 1 or a don't care. So this should be a 1 or a don't care. So instead of having to, you know, remember what you did in the past and you know, pull it out of the table, which is potentially error prone, and instead of having to reverse engineer the flip-flop, which is time consuming, let's just one time figure out how we set up J and K for different situations, and let's just write that down in a table, and then we can refer to it. The trick here is I don't want you to just think that this table is magic, and that, you know, I don't know what this table is, but you get the right answer when you use it, right? I want to make sure you understand why we can say, you know, 0, 1 or 0, 0 in this spot, and know that our output will go from a 0 to a 0. But once we figured that out, we can make a different version of a JK table that looks like this. And what I'm doing here is making a table which says if my flip-flop is currently outputting a 0, and after the clock ticks I want it to continue outputting a 0, what should I set J and K to? So I'm doing what we did when we filled in this, but I'm recording it in a separate table that we can use to fill in these columns in the future. So if we want the output to be a 0, we have two options. We could say 0, 1, which resets the flip-flop, or we could say 0, 0, which says don't change the flip-flop. So that's why this is a 0, don't care. And if we want the output to be a 1, and it was a 0, we can either say 1, 0 for a 1, or 1, 1 for toggle. So this is a 1, don't care. And if we want the output to be a 0, we could again say 0, 1 to force the output to a 0, or 1, 1 to say toggle the output. So this is a don't care 1. And if we want the output to be 1, we can either say 1, 0, force the output to 1, or 0, 0, don't change the output. So this is a don't care 0. So you'll see this in the book. Along with this, this is sort of the truth table of a JK flip-flop. But this is saying if we want the outputs to change from this to that, what should we set the inputs to? So this is sometimes called like an input excitation table or something like that. But we can write this by understanding what a JK flip-flop does. And we can use this when we fill in this state table. And that's all we're doing when we look for an example that we've already done. So for example, in this third row, the current value of Q0 is 1. The new value should also be a 1. We want to go from a 1 to a 1. Set your JK to don't care and 0. So this will be a don't care 0. So that's from a 1 to a 1, and this is a 1 to a 1. So same thing. And this is a 1 to a 1. And then this last row, we're going from a 1 to a 0, and that says set J to a don't care, K to a 1. So this will be a don't care and a 1. So questions about that part?
We would do that special current state next state JK table for both Q0 and Q1, right?
Correct, yeah. This is written basically to control what the new value of Q1 is, and then this is written to control the new value of Q0.
Looks like you're missing one there on
I am.
JZ.
Alright, so we want to go from a 0 to a 1, and a 0 to a 1 looks like a 1 and a don't care. So thanks for catching that. Well, here's the table for a toggle flip-flop. If T is 0, the output is unchanged. If T is 1, the output toggles. So we could also make our input excitation table for a toggle flip-flop. So suppose we have a T flip-flop. This is unrelated to the problem. This is a little sidebar question here. Suppose we have a T flip-flop, and it's currently outputting a 0, and after the clock ticks, we want the output to still be a 0. What should we set T equal to?
0.
Set it to a 0, because when you set it to 0, the output doesn't change. If it's currently a 0 and we want the output to be a 1, what should we set T to?
1.
Set it to a 1, because if it's 1, the output will toggle, and that's what we want. It's a 0, we want it to toggle to a 1. And if the output's a 1 and we want the new output to be a 0, we again want it to toggle, so we'll set T equal to 1. And if it's currently outputting a 1 and we still want it to output a 1, we don't want it to toggle, so we set the T input to 0. And if I happen to have a D flip-flop, it's the easiest of all. If I want my output to be a 0, set D to 0. If I want my output to be a 1, set D to 1. Here's the really cool thing for the homework, right? All of this part of the table.
Put that back, please.
Say again?
Can you put that back, please?
Yeah.
Sweet, thanks.
Welcome. So all of this in the table is independent of the type of flip-flops we're using. This is just based on the state diagram. Present state, next state, input, output. These columns we wrote down because we were told we were using JK flip-flops, and really all we've got to do is look at present state, next state, look up the values for J and K. If I wanted to redo this problem with T flip-flops, I just need to add one more column for T1 and a column for T0. And how do I decide what the value for T1 is? Well, look at the value for Q1 and Q1 plus, and write down what the value for T should be. So I can add two more columns, T1, T0, and just fill those in using this input excitation table. And now I've got all the information I need to build my circuit with T flip-flops. And then if I want to use D flip-flops, what do? 2 more columns, D1, D0, and I fill in those values based on the current and the next value for Q1 and Q0. So if you get a wide enough sheet of paper, you can make one state transition table for all 3 questions. And it saves you having to rewrite this part again and again and again. It's your choice. If you can copy it in print or something, you can do 3 tables, but you could also just continue this, T1, T0, and then D1, D0. And now you got all the information you need for each different type of flip-flop you're going to use. Alright, so let's continue with JKs. And we'll take a break after we finish this up. This finishes pretty quickly from this point. So the next step is to write equations. So we want to say something like Z equals J1 equals K1 equals J0 equals K0 equals. And these should be functions of your present state and your inputs. So each of these should be some combination of Q1, Q0, X, or their inverses, ANDed, ORed, something like that, right? We're not going to use the next state in writing this, right? This was purely used to figure out what the inputs to our flip-flop should be. All right, so let's deal with Z first. Z is pretty straightforward. Can anybody see an equation for Z without having to do a K-map?
S11.
Q1, Q0.
Yeah, so we can AND Q1 and Q0. Yes, you're right. If we're in S11, then Z should be a 1. And we can tell we're in S11 because Q1 will be 0 and Q0 will be 1, and Q1 will be 1. So Z is just Q1, Q0. And if we did a sum of products, right, it would be Q1, Q0, X bar, or Q1, Q0, X. And then if you put that into K-map, the X will go away and we'll end up with just Q1, Q0. So for these others, let's do a quick K-map. And I'm going to reuse the same K-map while we're recording this. Alright, so let's look at J1. So 0, 0, 0, 1, and then a bunch of don't cares. So I want to fill in my values for Q1, Q0, and so the way I've written my truth table, Q1, Q0, X, this will be my first row, second row, third, fourth, fifth, sixth, seventh, eighth. So maybe I'll ink these in very lightly. This is minterm 0, 1, 2, 3, and then 4, 5, 6, 7. The advantage of doing this is I can simply read down from top to bottom and fill these in, first, second, third, fourth, fifth, sixth, seventh, eighth. So I'm only going to put in my ones and my don't cares. So this is going to be 0, 0, 0, 1, don't care, don't care, don't care, don't care. And so how do I cover this with rectangles to make sure I cover all of the ones? What's a good cover?
You have the 4x4 at the bottom, and then you could drill the 1 in with a 2x1.
Okay, so I can pick up the 1 with a 2x1. And as soon as I do that, I've covered all of my 1s. And that's where you want to stop. I could cover the dashes with a 2x2, but I'm not required to. And if I draw another rectangle, I'm going to have another term. That's another OR gate. It's another input to an AND gate. So with don't cares, don't cover them unless it helps you cover the ones, which is why we're covering this don't care right here. So that's actually the whole covering for our K-map, and we just ignore these, which means we're basically treating them as zeros, but we're treating this as a 1.
Just X and Q not, or Q0.
So let's see, it looks like Q1 doesn't matter, it looks like X has to be a 1, and it looks like Q0 has to be a 1. So now we can write down an equation for J1, it's Q0X. And what we've done with these don't cares is we basically said, let's treat these as zeros, and let's treat this as a 1. Now that's perfectly valid. Why? Because we don't care whether these are zeros or 1s. But if we make this 0, 0, 0, 1, 0, 0, 0, 1, right, you can see as long as Q0 and X are 1, this will be a 1. And in the other cases, it'll be a 0. So this trick of using the don't cares and covering them or not covering them basically tells us how to fill in these don't cares in a way that makes it easy to write an equation. Alright, so I'm going to erase our boxes and let's do K1. And so K1 looks like 4 don't cares, and then a pair of 1s, and then a pair of zeros, which we don't write in. So for K1, this looks like our K-map. So what's a way to cover this optimally?
Wouldn't it be best to do it with connecting the top half and the bottom half?
I like it.
So you have a 2x2?
That looks really good. That's a nice big rectangle. It covers both of our 1s, but it's a bigger rectangle than just covering these two with a 1x2. Bigger rectangle, simpler expressions. So we don't care about these. We'll let those be zeros, but we're going to treat these as 1s. Awesome. So what's the equation for this rectangle?
Q0 not.
So Q1 can be a 1 or a 0, so that doesn't matter. Q0 has to be a 0. And X can be a 0 or 1, doesn't matter. So K1 is just Q0 not. And if you look at your truth table, Q0 not, well, that would be 1, 1, 0, 0, 1, 1, 0, 0. And that's satisfies what we've written, because we don't care about the 1, 1, 0, 0 here, but we got the 1, 1, 0, 0 that we do care about. So that's a great way to write K1. It's one inverter. In fact, we don't even need an inverter because our flip-flops have inverted outputs. So this is just a wire coming from Q0 not into the K1 input.
Couldn't you also just make that Q1?
If we made it Q1, then it would be 1s down here. So these ones would be good, and these we don't care about, but we'd end up with 1s down here in the last 2 rows. So that would be different from what we want.
Oh, okay.
And that comes out of the covering by looking at the fact that on these 2 spots, Q1 is a 1, but on these 2, Q1 is a 0. So Q1 doesn't factor in. Now if we had done a covering of just this, then we would have gotten Q1, Q0 not. And that would be another equation that would work. But we have to augment the Q1 with Q0 not to make those 1s and those zeros. All right, getting the idea? So you don't get to erase on your homework because I want to see your work, but I'll save the trees. So let's do J0. So 0, 1, don't care, don't care. 1, 0, don't care, don't care. So that's not a super fun one to cover. Actually, I said I wouldn't draw on the zeros, so we'll just leave those out. And we can't do as much as I'd like to do here, but we can certainly cover that one with a 2x1, and we can cover this one with a 2x1. Anybody see a better cover we could use? I think that's probably the best we can get.
I mean, you could circle the 4 don't cares, but why would you do that?
Yeah, we could circle that too, and that would be a nice small expression, but since we don't care about it, we won't. Alright, so what's the equation for this upper right 2x1 rectangle?
Wouldn't it just be 0?
This rectangle here? It can't be exactly 0 because we've got a 1 right here.
Wouldn't it be Q1 not?
So Q1 is a 0 in both of these. So yeah, so we write that as Q1 not. Q0 doesn't matter. And then we have to AND it with X because X has to be a 1. Everybody see that? And then how about this one down here?
It would be Q1 ended with X naught.
Perfect. So that's Q1 ANDed with X naught. So now we can write J0 equals Q1 naught X or Q1 X naught. Do you happen to know another name for this function?
XOR, right?
That's an XOR. So A XOR B means A is true and B is false, or A is false and B is true. So Q1 bar X or Q1 X bar. So we could build this with a pair of AND gates and OR them together, but that's exactly the same thing as an XOR. So if you have an XOR in your box, you can do it like that. Make your circuit a little simpler. And the hint to think about XORs is when you've got diagonals going on, or checkerboards, play around with an XOR truth table, see if it looks like it might work for your equation.
I mean, you still don't get it wrong if you keep it in the unsimplified.
Right, right. But if you're going to build this and you're not told that you're not allowed to simplify, you definitely want to simplify, because it's a lot of circuitry. Alright, this one may be more glorious. So let's take a look at K0. And so K0 looks like don't care, 0, 0. 0, 1, don't care. Oh, not super glorious. You know, if we had a don't care there, we could just like, boom, do like a nice 4x1. So what's our best cover here?
Just a 1x2.
A 1x2. And you got a choice. You could do this, or you could do a broken one. Different equations, but identical complexity. So if we do this one, that looks like Q1X. But you could also do this one. And that would look like Q0 bar and X. So either one of those, but we don't need to do both. So I'll just go with the original one here and just say Q0 equals Q1X. All right, there's your equations. And now you just sketch a circuit. And we can do this similarly to how we sketch circuits, you know, with inputs and logic and outputs. We can organize this. It takes some fiddling around sometimes, but let's go ahead and just outline what a circuit would look like. And I'll do this in pencil because I'm bound to mess up somewhere. So let's make a flip-flop. And it's got a JK input. J0, K0, Q0, Q0 bar. And I'll put another one here. Yeah, I'll put it next to it. J1, K1, Q1, Q1 bar. And I'm going to run these outputs vertically. And I'm going to feed these inputs. I always think this is going to be like beautiful. It never ends up quite as elegant as it is in my head, but we'll try it again. Alright, so let's make circuits for our equations. So first of all, Z is Q1 ANDed with Q0. Well, that one's pretty easy. Here's Q1, here's Q0. Let's put those through an AND gate. There's Z. So that's the output of the circuit. Alright, let's do J1. That's Q0 ANDed with X. So we have an input somewhere, X. So let's just bring that in like this. And then let's invert it. And bring that down there. So we've got X, X bar, Q0 bar, Q0, Q1 bar, Q1. Those are all the things we need to combine to produce our flip-flop inputs and our output Z. So let's do J1, Q0 ANDed with X. So I'll do Q0 and X. And I'll AND those. And that should feed J1. So we've built that part of our circuit. K1 is just Q0 bar. So I'm just going to tap into Q0 bar and bring that over and connect that right up here, which feeds into K1. And we'll take off that little piece there. Alright, J0 is Q1 XORed with X, or Q1 bar X, or Q1X. Let me do this one just because we're in a groove now, and let's make our circuit look super duper fancy. So we'll do Q1 bar X. So here's Q1 bar, and here's X. And let's AND those together. And then let's do Q1 ANDed with X bar. So here's X bar. And here's Q1. There's my banana fruit fly. And we want to take those and OR them. So we'll put those into an OR gate. And that's going to be J0, which is right here.
Wouldn't that be an XOR gate though?
So I could do it as just an XOR of two inputs, but I said let's just go ahead and write it out. In case you didn't notice that it was an XOR, you could do it like this. But you're absolutely right. I could also just take Q1 and X and put them through an XOR. And then K0 is just Q1 ANDed with X. So here's Q1. And here is X. And we'll AND those. And that's going to come up here and wrap around and feed into K0. And so that's that equation. And then the last thing to do is just tie your clocks together. And there you go. There's your state machine that generates this diagram. And it only took us 1, 2, 3, 4, 5 pages of paper to do that. So these are lengthy. Yeah, I was being facetious. These are long problems, right? The most important thing is trying to understand each step, right? And it's a long process, but hopefully, you know, each piece of it is a relatively small step from the previous one. It's just that there's a lot of steps, right? But every state machine problem that you encounter where you're trying to synthesize a machine is going to go through the same sequence of steps. You get a diagram, or you get a description of a machine and you draw a diagram, right? You decide how many flip-flops you need. And if we're doing what's called full encoding, we use as few flip-flops as necessary. 4 states, we only need 2 flip-flops. And then you decide what kind of flip-flops to use, or you're told what kind to use. You come up with a mapping from combinations of flip-flop values to the different states. That's our state assignment table. And then you start the kind of heady part of it, which is making your state transition table. And that you can use these input excitation tables if you want, or you can use the response tables for these flip-flops and figure out what goes in those inputs. But you fill out this, and then you go through the process of writing equations for these. And this would have been more than 5 pages because I reused this K-map 5 times, so it would have taken more sheets than 5. But you know, you go through and you use K-maps to write equations for each of these flip-flop inputs and for the circuit output. And then finally you take those equations and you sketch a circuit from it. And then there's your solution for that machine. So 3 questions, but remember, this table is reusable for all 3 parts. You can simply continue this and put in your D1, D0, and T1, T0 for the D and T flip-flop implementations. This you only need once, right? You can use the same state assignments in each case. This table of inputs for different excitations you can use for all 3 of those. So those don't get replicated. You have one big wide table if you like for all 3, or like I say, you know, if you have access to a scanner and a printer, you can, you know, make this once and print it out 3 times. Or if you have carbon paper, you know, you can go old school, and then just read.
Digitally if we want.
You can do it digitally if you want, but don't get lost down a rabbit hole of trying to coerce Excel into making tables for you or things like that. But yeah, if you want to do it digitally, that's totally fine.
Word table insert, that's pretty dang easy to use. I recommend it for this kind of thing.
Cool. Yeah, just play around with it first if you haven't done it before, so that you know how to do things like, you know, add an extra column or insert a row if you missed one or things like that. But yeah, that can work well. And so this is where you're going to spend a lot of sheets of paper, is writing the equations, because you know, you're going to need a K-map for each of your inputs to your flip-flops. But for toggle flip-flops, you only have two inputs to worry about, T1, T0, and your output's not going to change, right? So your equation for your output's going to be the same in all cases. So that's done once and done. So yeah, definitely, probably not 15 pages necessarily, but you know, this worked plus maybe a few more pages depending on how much you reuse, and then you know a separate circuit for each one. That will obviously be totally different because it depends on your equations. All right. Well, we only got 20 minutes left, but let's go ahead and do a 5-minute break or 4-minute break, and then we'll talk about this business of one-hot encoding versus full encoding, which is not on the homework anymore, but I want to talk about it anyway because it's fair game for exams and stuff. So take a 4.5-minute break. We'll come back and finish talking about encoding. All right. So this business of encoding is related to this idea of a state assignment table. So in our previous example, we had 4 states, and we were using 2 flip-flops, flip-flop 1 and 0, and we looked at their output values, Q1 and Q0, and different combinations of those corresponded to different states. And that's what we call full encoding, because we're considering basically all possible combinations of those individual flip-flops outputs. Now suppose we have a machine like this where we have 2 states, and let's say we're using JK flip-flops, and we want to make a state assignment table. So we could have a state, and our state could be S0 or S1. And we know that we could do this by using a single flip-flop. We could use one flip-flop, and we could say, you know, we'll just call that Q0, and a 0 means state 0, and a 1 means state 1. Okay, that's using full encoding. But there's an alternative. We could use 2 flip-flops. We could use a pair of flip-flops, Q1, Q0. And we could say state 0 is going to be represented by this pattern, and state 1 will be represented by this pattern. Now, why would we want to do that? Why would we want 2 flip-flops instead of 1? It turns out that we can avoid certain race conditions sometimes by doing this. Because what we're going to do is basically say the following. So 0, 1, that's state S0, 1, 0, that's state S1. These are going to be considered invalid or don't care states. And if we are building circuitry that's going to move from one state to another, here's the situation. If we change from state 0, 1 to 1, 0, this bit has to change from a 1 to a 0, this has to change from a 0 to a 1. We don't know the order in which those things are going to happen. And it's possible that if we're in state 0, 1, we could then change to state 0, 0 as this changes from a 1 to a 0, and then eventually this 0 becomes a 1. And we have this intermediate state here. Or it could be that this bit changes first from a 0 to a 1, and then this second bit changes from a 1 to a 0. And we have this intermediate state. And if this is a meaningful state, if this is a state that says, you know, some condition has happened, take some action, we're changing from state 1 to state 2, but we've temporarily triggered something that happens in state 3. But if this is recognized as an invalid state, and this is an invalid state, then we can build a circuit that won't inadvertently do something wrong when it goes from, say, state 1 to state 2. So if we code all of our states in such a way that only one bit is allowed to be a 1, then if we go through these transient states in between, they'll just be considered invalid states. And typically we would set our outputs to make sure that you know, nothing weird happens in that case. So sometimes we'll use one hot encoding if it's critical that we know that the system is always in a only in a valid state. It takes more hardware because we have to use more flip-flops, and it's more complex to build it. But when we make our truth table, we're going to find a lot of don't cares, because a lot of these states are considered invalid. So we might make a truth table like, you know, present state Q1, Q0, and our input X. And we'd have some output Z, and we would put it in some do no harm state for these illegal states. So let's go ahead and name these states. So these are illegal states. This is S0, this is S1. That's an illegal state. So maybe we'd set our output to 0 in these cases. And I didn't put outputs in here. There's some outputs. So in state 0, we would leave the output as a 0. But in state 1, we'd leave it as a 1. And then if we try to fill down the next state, right, these would be don't cares. Because we don't consider this a valid state. It's a transient state the system might go through, but if it's in that state, we don't care what the next value is going to be, because you know, it's not going to enter this state unless it's in this state and the clock ticks, and we never expect it to be in this state or that state. So we'll end up with don't cares in here, and if we don't care what the new value of Q1 is, then we certainly don't care what the J and K inputs are. So all of these will all be don't cares automatically. And so even though we've got more flip-flops, the equations end up not being too bad. They're pretty harmless. All right. Questions about any of that? I'll show you just for fun the traffic light experiment. We used to actually have students build this in hardware, and there was one year when we actually had people optionally program a piece of programmable logic, a field programmable gate array, and use that to implement the three-way traffic intersection light with red, green, and yellow lights. And for people who did that, there was a test bed. So I built this up a long time ago when I was first at Clark, and it's this little three-way intersection. And we had 3 cars. There was a Camaro, a Mustang, and a Corvette. And there were little sensors under here, and there were magnets in the cars. And if you put a car in the intersection right before the stop line, it would trip a sensor, and you could tap into those sensors on this proto board. And so students would program their circuit in this FPGA connected to the proto board, and then it would actually tie into these lights on the intersection. So you could actually put a car there, and if that car had priority, you'd see the neighboring light turn yellow and then red, and then this light would turn green. And so that's like a physical test bed that you would use to plug your circuit in, set up inputs, in this case by putting cars there, and then look at outputs, in this case in the form of LEDs. And that's
an FPGA you can buy?
That's an FPGA you can buy. We have a bunch of them at Clark that we used to loan out for the lab. But they're actually really inexpensive. They're like $30-some from Amazon, so we ordered a bunch of them. And it's a pretty hefty FPGA. And this uses a set of software from a company called Xilinx, a package called ISE Webpack. It's a moving target. Every time that I did this, I had to go in and rewrite the tutorials and the how-tos because the software keeps changing and so on. And we won't get to that in this class, unfortunately, but we will talk about the language that we use to program FPGAs, which is something called Verilog. And then, yeah, if we were back in class, we could actually like do this with physical hardware, which is a lot of fun. But, you know, once we're back in, if you're still at Clark, you can always go into the collaboratorium and get one of these boards and play around with it and have some fun with it. Or as you move on to your 200 level engineering or CS courses, part of what you'll be working on is a year-long project called a Service Learning Project. And I've had students who have used FPGAs and Verilog and things like that as part of their year-long project. So there's opportunities for that. If you're going WSU, there's an embedded systems course you can take as an elective your last year, and that would get you into playing with FPGAs and stuff like that. So there's the interface board that we had, and there's what the FPGA itself looks like. And it's you program it through a USB port, and it's got, you know, a gazillion pins on it, and these are mostly I/O lines, and you can load your circuit into it, and it will, you know, take inputs, generate outputs, and it's a more modern way of building a circuit as compared to using a proto board. So we'll spend a few more a bit more time next week on Tuesday, probably wrapping up state machine synthesis. Your homework's not due till Wednesday, so hopefully there'll be questions on that last homework and questions on the lab. The lab will go on for another week, but after we're done talking about state machine synthesis, we're going to start talking about programmable devices and Verilog, this language that we can use for programming these kinds of things. We'll be working in simulation instead of using physical hardware, but the simulator in some ways, you know, is always a step of the process. You design your circuit, you write Verilog, you put it into the simulator, and it will show you what the circuit would do. And then this would just be an extra step of saying, okay, let's go ahead and program the chip and actually hook it up. So we'll start that, you know, either Tuesday or Thursday. We'll begin down that path. This is the end of week 7, so we've got 3 weeks left after this, 8 through 10. And we'll spend most of that playing with Verilog and then kind of wrapping up, picking up a few loose ends at the end and so on and so forth. So that's pretty much it for this week. So keep working on the homework, keep working on the lab. Bring questions to office hours tomorrow if you like. And otherwise, have a good rest of the day, good afternoon, good weekend, and I will see you next time.